For over 50 years, every high-performance car on Earth has been built around a rule so fundamental. It stopped being questioned. If you want grip, you need wings. If you want speed, you accept drag. It wasn't a design philosophy. It was treated like physics itself. But what if that law was never actually true? What if the rear wing, the most iconic symbol of performance, was just an engineering workaround for a deeper limitation no one could solve? Because in 2026, something appeared that shouldn't exist. A machine with no wing, no compromise, and no respect for everything the automotive world believed in. And once you understand how it works, you realize the industry didn't just hit a breakthrough, it hit a reset. To understand why this moment matters, we need to go back to where performance engineering truly began to evolve. Because speed was never just about power, it was about control. By the late 20th century, engineers had already reached a critical realization. Increasing horsepower alone didn't make cars faster around a circuit. In fact, it often made them harder to control. More power meant more instability, especially when cornering at high speeds. So the focus shifted. Instead of chasing raw output, engineers began to chase grip. And that led them directly into the world of aerodynamics. Air, which had always been seen as resistance, became something else entirely. A tool. And if you could shape airflow correctly, you could push the car into the ground without adding weight. This was the birth of downforce. At first, it was simple, small spoilers, basic airflow redirection. But as racing evolved, especially in Formula One and endurance racing, aerodynamics became a battlefield of precision engineering. Every surface mattered. Front splitters were designed to manage incoming air. Side skirts sealed pressure zones. Diffusers accelerated airflow beneath the car, and at the center of it all, the rear wing. The wing became the ultimate solution. By creating a pressure difference between its upper and lower surfaces, it generated a powerful downward force. The faster the car moved, the more effective it became. But there was a cost. A massive one, because every time you generate downforce this way, you are also creating drag. The wing doesn't just push the car down, it pulls it back. And this is where the industry made a quiet decision. They accepted the trade-off. More grip means more drag. More stability means less efficiency. And for decades, that compromise defined performance engineering. Cars became faster, but never free from that limitation. Even today, the most advanced hypercars, machines built with millions in wind tunnel testing, are still operating within that same framework, optimized, refined, but fundamentally constrained. And so the real question isn't how far this philosophy has taken us, it's why no one ever truly tried to escape it. At extreme speeds, air stops behaving like a fluid you move through. It becomes something you fight. At 300 kilometers per hour, airflow no longer glides smoothly across the surface of a car. It separates. It collapses into turbulence. It forms chaotic vortices that grow in intensity the faster you go. And once that happens, something else emerges. Drag. Not just simple resistance, but a force that increases exponentially with speed, consuming energy and limiting performance. But here's the paradox. The very systems designed to create downforce are also responsible for creating this drag. Rear wings, for example, work by redirecting airflow, and they force air upward, and in return, the car is pushed downward. It's a direct application of Newton's laws. But redirecting air requires energy, and that energy comes at a cost. Every unit of downforce generated through this method is paid for in forward resistance, relentlessly. This isn't a design flaw, it's a physical limitation, and engineers have spent decades trying to minimize it. They introduced multi-element wings to increase efficiency. They developed active aerodynamic systems that adjust in real time. They refined diffusers to extract more performance from airflow beneath the car. Each step brought improvements, but none of them removed the core problem, because all of them rely on the same principle: manipulating airflow externally. And that introduces another issue: complexity. Modern performance cars are no longer simple mechanical systems. They are networks of interdependent aerodynamic components that must function perfectly together. If airflow is disrupted at the front, it affects the entire system. If the rear wing loses efficiency, balance is lost. If turbulence forms unexpectedly, the car becomes unstable. And at high speed, instability is not gradual. It's immediate. A slight loss of downforce at 250 kilometers per hour isn't a small issue. It's catastrophic. But the most dangerous problem is one that is often overlooked. The external aerodynamics are exposed: crosswinds, road conditions, airflow disturbances from other vehicles. All of these can disrupt the delicate balance engineers work so hard to create. And when that balance breaks, grip disappears instantly. So after decades of refinement, the industry reached a silent conclusion. External aerodynamics had reached its limits. It could be improved, but it could not be fundamentally redefined unless someone stopped trying to control air from the outside and started designing the car around it. This is where everything changes. Because instead of adding more aerodynamic components, this new approach removes the assumption that aerodynamics must exist outside the car and replaces it with something far more radical. The entire vehicle becomes the aerodynamic system. This idea originates from aerospace engineering, specifically the concept of a lifting body. In advanced aircraft design, the fuselage itself generates lift, eliminating the need for large wings. Now imagine reversing that concept. Instead of creating lift, you create downforce, but not by pushing air, by accelerating it. As air is forced through ultra-narrow internal channels within the vehicle's structure, its velocity increases dramatically. And as velocity increases, pressure decreases, a direct application of Bernoulli's principle. This creates a massive low-pressure zone beneath the car. And that pressure difference generates downforce. Not through resistance, but through flow. The car is no longer being pushed down. It is being pulled down. And that distinction changes everything. Because pulling air through controlled pathways is far more efficient than deflecting it with external structures. Less turbulence, less drag, more stability, and significantly higher aerodynamic efficiency. But the innovation doesn't stop there. At high speeds, airflow becomes unstable, especially during cornering. Lateral forces can disrupt the pressure zones beneath the car, leading to a sudden loss of grip. To counter this, advanced airflow management systems are introduced. Microscopic channels manipulate the boundary layer, controlling how air behaves as it exits the vehicle. Vertical stabilizing elements help maintain directional stability. Even the wheels are redesigned. Instead of disrupting airflow, they actively manage it, pulling cool air inward, expelling heat outward, all while preserving aerodynamic integrity. This is no longer passive aerodynamics. It is active airflow control. The car doesn't just move through air, it shapes it, continuously. For decades, companies like Ferrari, Porsche, and McLaren defined the limits of performance engineering. They mastered aerodynamics, perfected it, pushed it to its absolute edge. But they did so within a system built on compromise. More downforce always meant more drag. More control always meant less efficiency. Now, that assumption is being challenged, because if a machine can generate more grip, with less drag, without relying on wings, then this isn't competition. It's disruption, not evolution. Replacement. And that forces a difficult question. If the foundation of performance engineering changes, what happens to everything built on top of it? For decades, the wing was more than just a component. It was a symbol, a visible expression of speed, power, and engineering mastery. But symbols don't last forever, because engineering doesn't stand still. It evolves, and sometimes it replaces everything that came before it. Because what we are seeing now is not just a faster machine. It's a different philosophy, one that doesn't fight physics, but works with it. No external force, no visible struggle, just controlled airflow, doing the work more efficiently than ever before. And that changes everything, because if performance no longer depends on compromise, then the entire industry must adapt or fall behind. The wing is no longer the future, it's the past, and what comes next is already here.